Well, the zombies are off to their day job, which I'm not sure what that is, to be honest with you. So this is supposed to be an analogy for the rate determining step. When the doors open on the subway, there are 5 exits, and so the zombies can get out really rather quickly through these 5 exits. Now, to get off the platform, there's only one staircase, and so that's a bit of a bottleneck there. That's slowing them down. But once they leave the station, there are 4 exits, and once again they can leave with greater ease. So this is an analogous situation to the rate determining step. The slowest step is the one that governs how fast things happen. And in this case, the staircase was the slowest step. And so if you wanted to improve how fast zombies could leave the station, you'd have to add another staircase. Adding more train doors or adding more exits from the station would do no good. So let's look at a real chemistry example. The equation at the top and the mechanism below, well, that looks just like the equation. So the mechanism is just one step. A hits B2 and makes AB and B. It's a one-step mechanism. The IB wants you to know 1 or 2-step mechanisms. So the rate equation, well, the rate equals, and then you need to put K for the rate constant. You can see the concentration of A is important because it's in the reactants. And you can see that also the concentration of B2 is important because that's also in the reactants. If I mess about with either of those concentrations, that's going to affect the rate. And so the rate equation allows me to visualize that. Now this is a very simple one, a very easy one, but it gets a little bit more difficult. Easy? Or too easy? Okay, this one, to be honest, is still easy. The equation's at the top and a possible mechanism I've outlined below. There's 2 steps to the mechanism. Now the first step is the rate determining step, and that's what you've got to look for. Try and find the rate determining step, which in the previous example was the staircase. That's the slow step, the one with the highest activation energy. There is another assessment statement about this that you can check out. Now the first step's the rate determining step. I'd probably have to be told that. Now let's see if the mechanism's actually going to add up to the equation at the top. Yep, I've added the mechanism up and that gives me the equation at the top. So it's looking good already. If they don't add up to that top equation, it's not the mechanism. Something's gone wrong. So once again, rate equals K, K being the rate constant. Now I have to look at the rate determining step and put the reactants in there from the rate determining step. Now I've put little 1s there. Maybe I'll put 1s, maybe I won't. The order of reaction for each of those reactants was 1. Well, this is a slightly more tricky one, a medium level one. Which mechanism fits the rate equation for that reaction? Well, there are 3 possible mechanisms. Now I have to look for the rate determining step, and I've not given that information yet. So as written, this is actually impossible. So I'm going to choose the top equation in the mechanism as the rate determining step. You have to be told that or it doesn't work. So remember, the rate determining step, that's the slowest step. So take the chemicals in the rate determining step and put them in the rate equation. Don't forget the K. Okay, so that's rate equals Ka squared. Okay, that fits. That's looking good so far. For the second one, take the reactants in the rate determining step, put those in the rate equation. No, that's not looking good. Don't forget the K. Everyone forgets the K. No, that doesn't fit the rate equation. And for the third one, there's only one step, so that must be the rate determining step. So the rate is KAABC. Now you could say A squared if you want. Not only does that not match the rate equation as given, it's also extremely unlikely. 3 things hitting together with energy greater than activation energy and in the correct orientation, that is almost unheard of in kinetics. And the IB likes to try and trick you with that by saying, could these 3 things come together? Extremely unlikely. Alright then, so we've discovered that the rate equation fits with that mechanism. I'm going to add up that mechanism and see if it comes out at the target equation at the top. Cancelling what appears on both sides, yeah. If I add up that mechanism, it gives me the top equation. So that's good. That mechanism fits. Might not be the right one, but it does fit the data given. Okay, this one's quite hard. Here the second step is the slowest. Now I thought we were looking for the rate determining step. Well, the slowest step is the rate determining step. So I'm going to put RDS next to that to remind me. Now again, rate equals K, and then put the reactants in the rate determining step. Multiply their concentrations. And there's your problem. This O, that isn't a reactant that I knew I put in. With this O, I didn't even know it was there. You can only have reactants in the target equation, not this weird intermediate. So how do I make this O? I'm not allowed to have it in there. Well, tracing it back through the mechanism, O is made by NO2. So where I see O in my kind of rate, I can replace it by NO2. So that gives me KNO2 squared. Right, this one's one of the trickiest questions they can ask. And it's not me that's obsessed with nitrogen, the IB always has nitrogen. So suggest two possible mechanisms, a one-step and then a two-step mechanism. Now the one-step's actually easy. It has to be the same as the equation as written. There's only one step, so that's probably got the highest activation energy, the only activation energy. Now, I've put the reactants into the rate equation. If you're confused where that squared comes from, allow me to write out a little clearer. So N2O appears twice, multiplied together, so that's just squared. And once again, I've done the mistake everyone else does, is I've forgotten to put the rate constant in. So it was wrong, but now it's right. The one step's quite straightforward. The two step, I don't claim to be able to teach this. I don't know how to explain it. There's always two sorts of answers. This one, and in 2 minutes I'll give you the other answer. So I'm just going to scribble out a two-step mechanism. You just have to mess around with it. But that's the format it normally takes. I'm going to just add up my mechanism, cancel what appears on each side. Yes, and that seems to equal the target equation. So we're halfway there. Now what is my rate determining step? The step with the highest activation energy. So let's choose the first one and see if that gives me the correct rate equation. So rate equals K, what's the reactants in that mechanism? N2O. Nope, that's not right. It doesn't match with the one stated in the question. Let's choose the second line in the mechanism as the rate determining step. So rate equals K. There's that O again. To be honest, it always seems to be an O. I'm not allowed to have that O. It's missing from the target, the initial equation. It's not a reactant, so it can't be in the rate equation. What makes O? Trace it back. N2O makes O. So substitute the concentration of O for the concentration of N2O. Yep, that's right. And the final one, give a two-step mechanism consistent with the rate equation there. Again, I don't know how to teach this, so just pause it and have a think. Well, there's the answer. If the top one's the rate determining step, the mechanism cancels. Yes, that's correct. So when they ask these evil questions, pull a mechanism out of your ear, it's normally one of those two that you've seen just now.